Hi and welcome to our motor control lab. Today we will take a look at Microchip's newest motor control reference design, high-speed trapezoidal BLDC control using AVR, showing you how we go from hardware assembly, programming, seeing some precise metering during real time, and spinning the actual motor. So some examples of end-use application for this demo are household or self-care appliances like leaf blowers, hair dryers, vacuum cleaners, and more. The reference design hardware consists of the AVR 16EB32 Curiosity Nano evaluation kit, the multi-phase power board, and an adapter board to connect them together. Power is supplied by an external source such as a lab bench SMPS. The selected motor is a 3-phase BLDC with either one pole pair or multiple pole pairs. A computer or laptop using serial communication software such as Thermal Data Visualizer is used to be connected to the C Nano using a USB to Type-C connector to visualize in real time the data acquisition of the output of AVR EB. The speed of the motor can be set by either using the potentiometer present on the MPPB board or an RC input PVM. More information about the hardware can be found on the GitHub page or reference design page.
Let's discuss the hardware changes. 3 capacitors must be added to the off-the-shelf board in order to reduce the impact of noise at the desired high-speed synchronization. The impact is a small delay added to the zero-cross detection, but this is compensated in hardware. The multi-phase power board has placeholder pads for the capacitor that need to be added. The block diagram depicts a total system solution approach where the microcontroller, the voltage regulators, the MOSFET drivers, and sensors are from Microchip. The internal peripherals are arranged efficiently to multiplex the back EMF signals coming from the motor into a single comparator. And notice how we are using only one shunt for current limit and measurement. The design is organized so that the MCU takes care of the communication, of the input interpretation, of the protections, of synchronizations, drive, and control. And also there is some spare memory and IOs left for more functionalities. When we take a look of the control strategy, we see that this is a simple drive algorithm and it's optimized for high-speed capabilities and fast response, where the high side is driven with PWM signals, while the low side focuses on state change without concerns about dead time. This allows for good synchronization timing during high electrical RPM speeds. The back EMF signals are proportionally divided and filtered with the capacitors mentioned in the hardware changes before they enter the analog comparator on the negative pin that is multiplexed, while on the positive pin, a virtual neutral will create the necessary comparison point. The virtual neutral is reconstructed in hardware using a net of 3 resistors and a capacitor. The drive sector position and feedback interpretation will dictate which back EMF channel is multiplexed to each sector. Now that we have the drive signals and we are acquiring the back EMF signals, for the best efficiency, the scope is to align in a controlled way the drive zero cross with the feedback zero cross. The phase advance can be different than 0 and it can be decided based on the end application, but the scope is to have it constant during the operation, even with load changes. To do synchronization and speed control, the library uses a proportional integral algorithm. The algorithm is simplified using only bit shifting operations, and it is lightweight so that a variety of 8-bit MCUs can handle the equation in time for the next PWM cycle. So, what are the capabilities of the library and what configuration are we allowed to do without breaking the algorithms and timings? The algorithms relevant to motor specifications are in configuration files separate from the API functions, which give the user an easy way to adapt to a desired motor. The library has the current features: configurable start ramp, current, voltage bus, and potentiometer analog measurements at runtime, switching frequency at 40 kHz, adjustable phase advance, PVM input for compatibility with radio control receivers, full support for peak over current, average over current, over voltage protection, and stall detection. The library has the common files folder for motor control algorithm and separate files for the used platform that links the low-level configuration to the motor control wrapper. The library layers have the scope of ease of use and simplicity so that the user can interact only with motor control level APIs without any worry about hardware level APIs. The motor control layer APIs include initializations, starting and stopping the motor, desired speed setting, and multiple returns of runtime values. If we look at the config.h file, we see that there is a division when it comes to what the configuration is related to. Thus, the library provides flexibility for the user in the application, the drive mode, board, and motor-specific settings. Programming the microcontroller is simple. Just download the project from the GitHub page, and then open the MPLAB-X IDE, click on File, Open Project, select the Motor Demo EB project, and after that, just simply click on the Make and Program device. And that's it. To see the data provided by the MCU, you can use the MPLAB data visualizer or any other serial communication tool. Just click on the data visualizer in MPLAB-X IDE, and then click the Settings button, and the connection details are UART protocol 8N1, and the baud rate is 57,600 BPS. After all the steps are completed, just click Start Capturing and Send to Terminal. And now you can see data acquisition output from the AVR EB in real time.
Turn on the voltage source with the desired voltage level suited for the used motor. Notice the LEDs turning on the power board. Now the hardware setup is ready to spin the motor. Set the potentiometer to a desired speed. Let's start with 50% as an example, and to start the library we must push the button. You could observe that the speed of the motor has increased or decreased based on the potentiometer value. Now let's take a small peek at the electrical signal modulation that goes to the motor and current signals as we apply some load changes. You will notice how the algorithm adapts with the load change to maintain motor synchronization and speed control. Now let us simulate the user's first use when they have a different motor connected to the hardware setup. Keep in mind that you have to change the motor-related values in the config.h file, recompile and program the board. Now that the library is updating on the MCU, we have to go again through the same steps. Push the button and change the desired speed with the help of the potentiometer. We can notice that the algorithm has adapted to the new motor and conditions without the change in the final result, which is the successful motor speed regulation.
Let's move on to the use cases section. This demo shows that the library can be used in real-life applications such as household high-speed appliances for both low and high voltage. Some examples include vacuum cleaners, hair dryers, air extractors, air purifiers, ventilators, gardening leaf blowers, bathroom hand dryers. Other use cases are drone motors, fans or pumps, and motors that have many pole pairs and need high electrical RPM. As this library needs precise position control and it has big load variations, it is not suited for applications where the motor spins slowly, at least not without mechanical gears, such as mixers, blenders, toothbrushes, hairbrushes, gardening tools, shredders, inkjet printers, vacuum robots, wheels, and etc.
That concludes our demo on motor control. Thank you for watching and feel free to reach Microchip team with any questions.